Tonight we're going to talk about the silence. Not the silence in this room, or the silence of a late night, or even the silence of deep ocean water, but the silence between star systems. The silence that has persisted for the entire history of radio astronomy. The silence that sits at the center of the most important unanswered question in science. The silence that, the more carefully you study it, the worse it gets. Before we get started, if you love exploring the deep mysteries of space and the universe as much as we do, take a second to subscribe or follow us on Spotify. It helps this channel reach more curious minds like yours. Now, let's begin. The nearest star to our Sun is Proxima Centauri. You've probably heard this before. What you may not have sat with long enough is what the distance actually means. Proxima Centauri is 4.24 light-years away. A light-year is the distance light travels in 1 year, and light travels at 186,000 miles per second. 1 light-year is therefore approximately 5.88 trillion miles. Proxima Centauri is 24.9 trillion miles from Earth. Let's make that number human. If you could drive to Proxima Centauri at highway speed 70 miles per hour without stopping, the journey would take approximately 40 billion years. The universe is 13.8 billion years old. You would need 3 universes worth of time to drive to the nearest star. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object in existence. It is currently about 15 billion miles from the Sun, well outside the heliosphere, travelling at roughly 38,000 miles per hour. At that speed, it would take Voyager 1 approximately 75,000 years to reach Proxima Centauri, if it were headed in that direction, which it is not. In 75,000 years, human civilization as we know it has existed for less than half that time. Agriculture was invented approximately 12,000 years ago. The oldest continuously inhabited city on Earth is perhaps 10,000 years old. This is the minimum distance between our solar system and anything else. This is the nearest neighbour. The galaxy is not a crowded place. The average distance between stars in the Milky Way disk, where our Sun sits roughly 26,000 light-years from the galactic centre, is approximately 5 light-years. Not 5 light-years to a habitable planet. Not 5 light-years to a star with planets. 5 light-years to the next star, whatever it is. If you shrink the solar system down so that the distance from the Sun to Earth, 93 million miles, is the thickness of a sheet of paper, then on that scale the nearest star is a stack of paper about 70 feet tall. The Milky Way, on the same scale, is a stack of paper 310,000 miles high, which is further than the Moon. That is what we are dealing with. Not vast distances in the abstract. Vast distances that are not traversable by anything we have ever built, or anything we could build with technology that realistically exists within the next several centuries. And into this vastness we have been sending signals, radio signals specifically, which travel at the speed of light. We have been doing this, intentionally and unintentionally, since the early 20th century. The first strong radio transmissions from Earth began around 1900, which means that a sphere of radio signals, expanding outward from Earth at the speed of light, has now reached a radius of roughly 125 light-years. 125 light-years sounds substantial, but the Milky Way is 100,000 light-years in diameter. Our radiosphere covers a volume of space equal to approximately 0.0003% of the galaxy's volume. We have barely whispered, and in that whisper, no one has whispered back. By the end of tonight, we will understand precisely why the silence is worse than it initially appears, why the math behind the silence is harder to explain away than the optimistic frameworks suggest, and why sitting with the silence, really sitting with it, changes something about how you understand the universe we inhabit. We should be specific about the history of the search, because the silence is not a vague impression. It is the result of 65 years of systematic scientific effort. Project Ozma, conducted by Frank Drake at the National Radio Astronomy Observatory at Green Bank, West Virginia, in 1960, was the first formal scientific search for extraterrestrial intelligence. Drake pointed the 85-foot Howard E. Tuttle radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened on the hydrogen line frequency for about 150 hours across several months. He heard nothing artificial. Project Ozma was the beginning. What followed was decades of searches with progressively more capable instruments, covering progressively more of the radio spectrum in the sky. The Ohio State University Big Ear Radio Telescope, operational from 1963 to 1998, conducted one of the longest continuous SETI programs in history. On August 15, 1977, a volunteer astronomer named Jerry Eman was reviewing printed data from the previous night's observations when he noticed a signal that stood out so dramatically from the background noise that he wrote the word "wow" in the margin of the printout. The wow signal, as it became known, was a narrow-band radio signal at very close to the hydrogen line frequency, with an intensity roughly 30 times above background noise, lasting for exactly 72 seconds, which was the full duration of the telescope's observation window as the Earth rotated. The wow signal has never been explained. Despite multiple attempts to redetect it from the same area of sky, it has never appeared again. The most likely mundane explanation is radio frequency interference from a human source, perhaps a satellite or terrestrial transmitter, but no specific source has been convincingly identified. The wow signal remains the most anomalous single detection in 65 years of radio SETI, and it remains unexplained. After Big Ear, the search expanded significantly. NASA funded a SETI effort called the High Resolution Microwave Survey beginning in 1992, which was cancelled by Congress after 1 year. The SETI Institute's Project Phoenix, which ran from 1995 to 2004, was the most sensitive targeted search ever conducted, examining approximately 800 sun-like stars within 200 light-years using some of the world's largest radio telescopes. It found nothing confirmed. The Allen Telescope Array, funded partly by a major gift from Microsoft co-founder Paul Allen and constructed in Northern California from 2004 to 2007, was specifically designed for SETI, the first large telescope primarily built for this purpose rather than adapted to it. It can survey a wide area of sky simultaneously across a broad range of radio frequencies. It has been operating for nearly 20 years. It has found nothing confirmed. Breakthrough Listen, announced in 2015 with $100 million in funding from Yuri Milner, is the most comprehensive SETI program ever funded. It has used the Green Bank Telescope in West Virginia, the Parkes Telescope in Australia, and the FAST Telescope in China, the world's largest filled aperture radio telescope, to conduct the deepest and broadest radio survey ever performed for artificial signals. By the mid-2020s, Breakthrough Listen had surveyed over 1 million stars, analysed petabytes of data, and detected thousands of interesting signals requiring investigation. Every single one has been attributed to human radio frequency interference or natural astrophysical phenomena. None has been confirmed as extraterrestrial intelligence. The optical SETI program has run in parallel. Rather than radio waves, optical SETI searches for nanosecond laser pulses, the kind that a technologically advanced civilization might use for high-bandwidth interstellar communication. A nanosecond laser pulse bright enough to outshine the host star for a nanosecond would be detectable across interstellar distances with current technology. Multiple programs have scanned the sky for these events. No confirmed detection. The silence is not a result of not listening. It is the result of 65 years of listening with progressively improving instruments and hearing nothing. The null result is one of the most carefully accumulated null results in science. No one predicts, from within the scientific community that conducts these searches, that the silence is meaningless. The people who spend their careers searching understand exactly what the continued silence implies, and they continue searching precisely because the alternative, not searching, tells us even less. Let's talk about what actually fills the space between stars, because most people's intuitions about it are wrong in an instructive way. The interstellar medium is the material that occupies the space between stellar systems. It is not empty. It contains gas at extremely low densities, primarily hydrogen and helium, with trace amounts of heavier elements. The average density of the interstellar medium in the galactic disk is approximately 1 atom per cubic centimetre. To put that in context, the air you are breathing right now contains approximately 27 quintillion molecules per cubic centimetre. The interstellar medium is about 27 quintillion times less dense than air. It also contains dust, not household dust, but microscopic grains of carbon, silicates, and ice, roughly 0.1 to 1 micrometer in diameter, at a density of 1 grain per million cubic meters or so. These dust grains are enormously significant despite their tiny density. They scatter and absorb optical and ultraviolet light, which is why the center of the galaxy is hidden from optical telescopes. The galactic center is behind enough interstellar dust that the optical light from its billions of stars is reduced by a factor of 1 trillion before reaching us. We can only observe the galactic center in infrared and radio wavelengths, which are not blocked by the dust. There are also magnetic fields threading the interstellar medium with typical strengths of a few microgauss. These fields are coupled to the ionized gas in the medium and play a role in cosmic ray propagation, star formation, and the dynamics of the galaxy's disk. Cosmic rays, which are high-energy charged particles, travel along and across these fields, filling the interstellar medium with a diffuse radiation environment. What is remarkable about all of this is that it means interstellar space is not a passive void. It is a dynamic environment with its own physics, its own structure, and its own history. The atoms floating between stars are the remnants of supernovae, stellar winds, and planetary nebulae. Every atom in the interstellar medium was once inside a star, or formed in the aftermath of the Big Bang. The space between stars is filled with the dispersed exhaust of stellar processes going back billions of years. But for our purposes tonight, the most important property of the interstellar medium is that it is, at the scales we care about, essentially transparent to radio waves. A radio signal travelling from a civilization 1,000 light-years away would arrive at Earth almost without attenuation. This is why radio astronomy is possible. The galaxy's radio environment is not silent because signals cannot propagate. It is silent because, as best we can tell, no one is sending them. There is an exception worth noting, the hydrogen line. Neutral hydrogen atoms emit a very specific frequency of radio radiation at 420 MHz with a wavelength of 21 centimeters. This emission occurs when the electron in a hydrogen atom spontaneously flips its spin. It is an extremely weak transition, but there is so much hydrogen in the galaxy that the 21 centimeter line is one of the strongest radio signals we detect from space. It is so fundamental, so tied to the most abundant element in the universe, that radio astronomers and SETI researchers have long considered it the most likely frequency for interstellar communication. Any civilization in the galaxy that understands basic physics would know the 21 centimeter line. It is as close to a universal radio address as the physics of the universe provides. We have been listening on and near the hydrogen line since 1960. We have heard hydrogen, we have not heard anything else. The void between stars is not the obstacle to communication. Light and radio waves cross it just fine. The obstacle is the absence of anyone sending. That is the silence. And it is not a silence caused by physics. It is a silence that physics cannot explain. By the end of tonight, we will understand the full weight of what that means and why every proposed solution to the silence creates new problems almost as serious as the one it solves. We should understand the physics of interstellar communication in more detail, because it defines what is actually detectable and what is not, and it tells us precisely what kind of silence we are dealing with. Radio waves, like all electromagnetic radiation, obey the inverse square law. The intensity of a signal decreases as the square of the distance from the source. A signal that has travelled twice as far has 1/4 the intensity. 4 times as far, 1/16. This sounds punishing, but it is not as catastrophic for interstellar communication as it might seem, because modern signal processing techniques can extract signals from noise at extraordinary sensitivity. The question is not whether we can detect a sufficiently powerful directed signal, but whether any directed signal is being sent. The FAST telescope in China, with its 1,640-foot diameter dish, is the most sensitive radio telescope ever built. It can detect signals from interstellar distances at power levels that would be undetectable by earlier instruments. At the frequencies we search, FAST could in principle detect a transmitter comparable to Earth's most powerful existing radars at distances of several hundred light-years. A civilization that built a dedicated interstellar beacon, significantly more powerful than anything we currently operate, could be detected by FAST at distances of thousands to tens of thousands of light-years. This matters because it means the absence of detectable signals is not just about our instruments being too weak. If any civilization within a few thousand light-years of Earth were actively transmitting a powerful beacon toward our part of the sky, we would have a reasonable chance of detecting it with current technology. The continued silence is not obviously explained by instrumental limitations at these scales. The search has also expanded beyond radio. Laser communication offers significantly higher information density per unit of power than radio, and a sufficiently bright laser pulse, nanoseconds long, would briefly outshine its host star at optical wavelengths. Multiple optical SETI programs have scanned the sky for these pulses. They are sensitive to laser events at stellar distances. No confirmed detections have been made. There is also the question of leakage radiation. Earth's television and radar transmissions have been leaking into space since the 1940s. A sphere of human radio noise now extends about 80 light-years in all directions. Could an advanced civilization detect our leakage? Current calculations suggest that our strongest leakage signals, like military radar, could be detected by a telescope the size of the Arecibo dish at distances of a few light-years. Our broadcast television signals are too weak to detect at even the nearest star with anything like current technology. So we cannot rule out the possibility that nearby civilizations are as radio quiet in their leakage as a civilization somewhat more technologically advanced than us might become. Fiber optic communication, for instance, leaks no radio energy into space. This creates a specific form of the silence that is worth naming, the transition problem. A civilization that uses radio communications for its domestic purposes will leak radio energy into space during its radio era. But as technology advances, internal communications may shift to non-radiating media. The radio era of a civilization might be geologically brief. Our own radio era may be winding down as wireless communications shift to technologies that are more efficient and less prone to signal dispersion. If civilizations typically have radio eras of a few centuries at most, the probability that any two civilizations have overlapping radio eras at any given moment is very small. However, this does not explain the absence of deliberate beacons. A civilization that is no longer leaking radio energy domestically could still choose to maintain a dedicated interstellar beacon at a known frequency, precisely to make itself detectable to emerging civilizations. The transition problem reduces leakage but does not eliminate the paradox for deliberate transmissions. The search space that has actually been covered is also worth characterizing honestly. Breakthrough Listen has examined more than 1 million stars. The Milky Way contains between 100 billion and 400 billion stars. Even the most comprehensive search to date has covered less than 0.01% of the galaxy's stars. At the same time, if even a small number of civilizations had built galaxy-scale megastructures or beacon networks, those would be detectable in wide-field surveys regardless of whether we had pointed a telescope at their home star. The physics tells us Communication is possible across interstellar distances. Our instruments are sensitive enough to detect deliberate transmissions from a substantial fraction of the nearby galaxy, and we have found nothing. The silence is real, it is measured, and it is not explained by instrumental limitations alone. Absolutely no one anticipates that covering more of the search space will be irrelevant. Each new search either finds something, which would be transformative, or deepens the silence, which would be informative in a different way. Either outcome tells us something profound about the nature of the universe and our place in it. Tonight we're going to do the math that makes the silence hard to ignore. The Milky Way contains somewhere between 100 billion and 400 billion stars. Of those, estimates from the Kepler Space Telescope's planet surveys suggest that roughly 1 in 5 Sun-like stars has a planet in its habitable zone, the region where liquid water could exist on the surface. There are approximately 40 billion Sun-like stars in the galaxy. That gives us roughly 8 billion potentially habitable planets around Sun-like stars alone, without counting the much more numerous red dwarfs, some of which also have habitable zone planets. The galaxy is approximately 13.6 billion years old. Our Sun is 4.6 billion years old. Many stars significantly older than our Sun exist in the galaxy, which means planets around those stars have had billions more years than Earth has had to develop life, and, if life does develop, intelligence. If even a very small fraction of those potentially habitable planets around older stars develop technological civilizations, those civilizations would have had billions of years of head start on us, not decades, not centuries, billions of years. A civilization that is only 1 million years more advanced than us, a blink in galactic time, has had 1 million years more than we have had to develop space travel, to spread through the galaxy, to build transmitters, to do anything that leaves a detectable trace. At speeds much lower than light, a civilization expanding outward from its home system at even a few % of light speed could colonize the entire Milky Way within 10 to 100 million years. 10 to 100 million years is a tiny fraction of the galaxy's 13.6 billion year history. A civilization that started expanding even 500 million years ago should have reached every corner of the galaxy by now, and yet, nothing. This is the Fermi paradox, named for the physicist Enrico Fermi, who is said to have raised the question during a lunch conversation at Los Alamos in 1950. According to one account, the conversation had moved on to other topics when Fermi suddenly asked, "But where is everybody?" His colleagues understood immediately what he meant. The numbers say the galaxy should be teeming with technological civilizations. The observations say it appears to be empty. The contradiction between those two things is the paradox. Fermi's question was informal. The formal version came in 1961, when the astronomer Frank Drake developed what is now called the Drake equation, a framework for estimating the number of communicating technological civilizations currently active in the Milky Way. The equation multiplies together estimates of the rate of star formation in the galaxy, the fraction of stars with planets, the fraction of those planets in the habitable zone, the fraction of habitable planets where life actually develops, the fraction where intelligent life develops, the fraction where that intelligence develops technology that produces detectable signals, and the average lifespan of such a civilization. Most of these terms are genuinely uncertain. Life has only been observed on one planet. Intelligence has only been observed on one planet. Technological civilization producing radio signals has only been observed on one planet. The final term, the lifespan of a communicating civilization, is perhaps the most uncertain of all, because it depends on whether civilizations tend to destroy themselves, go silent for unrelated reasons, or persist and continue communicating. What is not uncertain is the first term. Star formation is well measured. Planetary occurrence rates are now well constrained by Kepler and TESS data. The fraction of stars with planets is close to 1. The fraction with potentially habitable planets is at least a few % and possibly much higher. The early terms of the Drake equation are, in 2024, much better constrained than they were in 1961. They are all relatively large. The entire weight of why the galaxy appears empty therefore falls on the biological and sociological terms, the fraction of habitable planets where life develops, the fraction where intelligence develops, and the lifespan of civilizations. The silence tells us that at least one of these terms must be very close to zero, or that civilizations are extraordinarily short-lived, or that something we do not understand is suppressing the development or detectability of intelligence at a scale that encompasses the entire observable galaxy. No one expects a comfortable answer here. The math is not friendly. The silence is not a measurement error. Let's work through the Drake equation carefully, because the specific values researchers assign to each term reveal why the silence is so hard to explain. The equation, in its standard form, estimates n, the number of detectable civilizations currently active in the Milky Way, as the product of 7 factors: R star, the rate of star formation in the galaxy; Fp, the fraction of stars with planetary systems; Ne, the average number of planets per system in the habitable zone; Fel, the fraction of habitable planets where life develops; Fei, the fraction of life-bearing planets where intelligence develops; Fei ancestor, the fraction of intelligent species that develop detectable technology; and L, the average lifespan of such a civilization in years. In 1961, when Drake wrote the equation on a blackboard before a conference at Green Bank, most of these terms were pure guesses. Today, the first 3 are constrained by data. Star formation in the Milky Way produces roughly 3 new stars per year. Planetary occurrence rates from Kepler indicate that essentially all Sun-like stars have planets. The number of habitable zone planets per system is probably between 0.1 and 1 for Sun-like stars, higher for red dwarfs considered as a class. These first 3 terms, when multiplied together, give a rate of potentially habitable planet formation in the range of 0.3 to 3 per year. Over the galaxy's history, that gives between 4 and 40 billion potentially habitable planets that have had substantial time for life to develop. The terms we cannot measure are the biological and social ones, and they are where all the uncertainty lives. Fl, the fraction of habitable planets where life develops, is entirely unknown. We have one data point. Life appeared on Earth within the first few 100 million years after the planet's surface cooled enough to support it. This is encouragingly fast, which has led some researchers to argue that life may develop readily whenever the conditions are right. But one data point is not a sample. We cannot distinguish between life develops easily and quickly and we exist on a planet where life happened to develop quickly because we could only arise on such a planet. This is the anthropic selection bias. We cannot observe habitable planets where life failed to develop because those planets do not produce observers. The fraction of life-bearing planets where intelligence develops has the same problem. Intelligence evolved on Earth. But the history of life on Earth, which spans roughly 3.8 billion years, is dominated by single-celled organisms. Complex multicellular life only appeared in the last 600 million years. The specific lineage leading to human-level intelligence required a sequence of events: the development of the vertebrate body plan, the evolution of large brains in mammals, the specific ecological circumstances of the African savanna in the Pliocene and Pleistocene, the development of language and more that may or may not have been likely given the starting conditions. Evolution has no target. It does not inevitably produce intelligence. It produces whatever survives. Intelligence is just one survival strategy, and not necessarily the most common. Fc, the fraction of intelligent species that develop detectable technology, is perhaps the least uncertain of the biological terms, at least by analogy. If intelligence develops, the development of tool use and eventually radio-emitting technology seems to follow with some regularity on Earth, given the trajectory of multiple independent human cultures converging on similar technological milestones. But other intelligence on Earth, cetaceans and cephalopods in particular, has not developed radio technology despite being cognitively sophisticated, which suggests that the step from intelligence to detectable technology is not automatic. And then there is L, the lifespan of a communicating civilization. This term is the one that many researchers believe must be short to explain the silence. If L is measured in centuries rather than millions of years, then at any given moment the number of active communicating civilizations in the galaxy would be very small, perhaps just one, perhaps zero. Our own civilization has been producing radio signals for about 125 years. If civilizations typically produce radio signals for only a few centuries before going silent, either through self-destruction or through some technological transition that makes radio obsolete, then the Milky Way would be populated by brief windows of radioactivity separated by enormous silences, like fireflies flashing randomly in a vast dark field. If L is 200 years, and the galaxy has been producing civilizations for 10 billion years, the number of currently detectable civilizations is N equals roughly 3 times 0.5 times 0.3 times FL times FI times FC times 200. If FL, FI, and FC are each even as high as 0.1, N comes out to less than 1. Less than 1 does not mean impossible. It means that on average fewer than one civilization is currently detectable in our galaxy. We might be the first to have lasted long enough, or we might be in one of those unlucky moments when no civilization is currently broadcasting. The numbers are not friendly to the crowded cosmos hypothesis. They are, when honestly examined, more consistent with extreme rarity than with common life. Absolutely no one anticipates that these calculations will become less troubling as our data improves. The biological terms of the Drake equation will not be constrained to comfortable values by any foreseeable observation. We will either detect life elsewhere and update our estimates dramatically upward, or we will continue not detecting it and be forced to consider that the early biological terms may be much smaller than intuition suggests. Let's talk about where the Great Filter is, because the answer to that question has radically different implications depending on whether it is behind us or in front of us. The concept of the Great Filter was introduced by economist Robin Hanson in 1998. The idea is simple. If intelligence is not rare, and we observe no intelligence other than our own, then something must be filtering it out. Something, somewhere in the chain from simple chemistry to galaxy-spanning civilization, is either enormously unlikely or catastrophically destructive. Hansen called this the Great Filter. The filter could be at any point in the chain. The most optimistic placement is early, before complex life. If the transition from non-living chemistry to the first self-replicating molecules is extraordinarily unlikely, then most habitable planets may sit in a state of rich chemistry for their entire lifetimes without ever producing biology. This would mean life itself is the filter. If life is the filter, and we have already passed through it, then the absence of other civilizations does not predict anything terrible about our own future. We are simply extraordinarily lucky. The second candidate filter is the transition from simple, prokaryotic life, the kind that dominated Earth for its first 2 billion years, to complex eukaryotic life. The eukaryotic cell, with its membrane-bound nucleus and its mitochondria, may be an extraordinarily improbable event. If most planets with life are stuck at the level of microbial mats forever, the galaxy would be biologically occupied, but intellectually empty. The third candidate is the evolution of intelligence itself. Intelligence, as we know it, requires a large brain with high metabolic cost, social organization capable of transmitting learned knowledge across generations, the development of language, and a series of environmental pressures that favor these traits over alternatives. If any of these transitions is very unlikely, most planets with complex life may never develop anything communicable. Each of these early filter placements is optimistic for us, because it means the filter is already behind us. We have already passed the extraordinarily unlikely step. But there is another set of possible filter placements. The filter could be ahead of us. It could be that simple life, complex life, and intelligence all develop readily across the galaxy, and that the filter is something that destroys or silences civilizations after they reach a certain level of development. Nuclear weapons, engineered pathogens, artificial intelligence that becomes misaligned with its creators, climate destabilization, resource exhaustion, any of these, or some combination, could be the filter that every civilization eventually encounters and that most fail to survive. If the filter is ahead, then the silence is a warning, not a reassurance. It means civilizations like ours have consistently failed to navigate the transition to long-term technological stability. It means we are approaching something that has, repeatedly and without exception, ended or silenced every other civilization that reached our level. No one predicts, based purely on the silence, which of these options is correct. The silence is consistent with all of them. What the silence tells us is that at least one of them must be correct, or that our understanding of the situation is missing something fundamental. The weight of the late filter scenario is almost impossible to hold in full. If the transition to technological civilization is common, and we see no evidence of any technological civilization that has survived past a certain threshold, then survival past that threshold may be extraordinarily rare. It may be that we are at or near that threshold right now. Hansen's original paper framed this with a specific kind of clarity that has not lost its force. Either the steps to technological civilization are mostly empty, which means most of the chain from chemistry to radio telescopes is very unlikely, or civilizations that reach radio telescope technology do not persist. There is very little room between these two options if the silence is real and the galaxy is as old and large as it appears to be. The Fermi paradox has generated a substantial number of proposed resolutions over the decades since it was formally articulated. Let's examine the most serious ones, because understanding why each falls short is part of understanding the depth of the silence. The first and most popular resolution is simply that we have not searched enough. The galaxy is vast, radio signals weaken with distance, and our SETI programs have covered only a tiny fraction of the possible frequencies, directions, and signal types over a relatively short time. This is true as far as it goes, but it runs into the artifact problem we discussed earlier. A civilization millions of years old and capable of interstellar expansion would have had time to colonize the entire galaxy. We do not need to detect their radio signals to detect them. We would detect them the way we detect continents, by the fact that they are present and visible. The absence of any large-scale physical modification of the galaxy by an expanding civilization is harder to explain away than the absence of radio signals. The second resolution is that intelligent life is simply extraordinarily rare. This is sometimes called the rare earth hypothesis, articulated formally by Peter Ward and Joe Brownlee in their 2000 book of that name. The argument is that Earth is not a typical habitable planet, but an extraordinarily unusual one, with specific features: a large stabilizing moon, a Jupiter-like planet in the outer system that deflects most large impactors, plate tectonics driven by the right radioactive isotope abundances, a magnetic field, a precise orbital distance, and more that are each necessary for complex life and each improbable. If complex life requires all of these conditions simultaneously, then complex life may be extraordinarily rare even in a galaxy with billions of habitable zone planets. This is a serious argument and has genuine scientific support. However, it explains the absence of biological complexity, but does not fully explain the absence of even microbial life, which may not require all of these special conditions, and it requires that many of Earth's specific features, each of which might be unlikely with probability p, combine so that the overall probability p to the power of n is very close to zero. For different assumed probabilities, this either resolves the paradox or does not. The third resolution is that civilizations go silent before expanding. Perhaps all civilizations destroy themselves or transition to some form of existence that does not involve interstellar expansion or detectable signals. Nuclear war, climate collapse, engineered pandemics, or the development of artificial superintelligence that redirects the civilization's resources away from anything we would recognize as communication. All of these could silence a civilization without eliminating it. This is sometimes called the Great Filter being ahead of us, which, as we discussed earlier, is the most disturbing possible resolution. The fourth resolution is the zoo hypothesis, proposed by John Ball in 1973. Perhaps advanced civilizations know we are here and are deliberately avoiding contact to allow us to develop naturally, the way a nature reserve avoids disturbing the wildlife. The universe is effectively a zoo, and we are the animals. This hypothesis is difficult to falsify, which makes it philosophically unsatisfying. It also requires that every civilization with the capability to contact us has agreed to the non-interference policy, including civilizations that may have very different motivations, values, and decision-making processes. One defector from the zoo protocol, one civilization that decides to make contact, would break the silence. The uniformity of the silence is hard to explain by a voluntary protocol maintained by all possible civilizations. The fifth resolution is the dark forest hypothesis, popularized by Chinese author Liu Cixin in his three-body problem trilogy. In this framework, the silence is the result of deliberate concealment. Any civilization that broadcasts its existence risks revealing its location to a hostile civilization capable of destroying it. In a galaxy where resources are finite and intentions are unknown, the optimal strategy may be to remain silent and eliminate any potential competitor before it can become a threat. On this account, the silence is not puzzling. It is the equilibrium state of a universe populated by civilizations that have independently reasoned their way to the same conclusion: broadcast and die. The dark forest hypothesis is compelling as fiction and plausible as logic, but it has practical problems. For the universe to be a dark forest, civilizations would need to be both numerous enough that their interactions are likely and sufficiently resource-constrained to make competition rational. If civilizations are rare, the dark forest logic breaks down, and if civilizations can freely convert matter to energy through advanced technology, resource scarcity may not be a constraint. The sixth resolution is the transcension hypothesis, proposed by John Smart, which suggests that advanced civilizations do not expand outward into space but inward, into smaller and smaller scales of computation, eventually becoming undetectable to radio astronomy, because they are operating at quantum computational scales that do not produce large-scale electromagnetic signatures. This is possible, but, like the zoo hypothesis, difficult to evaluate scientifically. None of these resolutions is entirely satisfying. Each explains part of the silence by introducing assumptions that themselves require explanation. The honest position is that we do not know why the galaxy appears empty. What we do know is that it appears empty, and that this appearance persists under increasingly rigorous examination. No one expects a resolution that is both simple and comforting. The possible explanations split between "we are extraordinarily rare" and "something eliminates or silences civilizations," neither of which is a pleasant conclusion. This silence is not a mystery that better technology will dissolve. It is a genuine feature of the universe as it presents itself to observation. The nearest star systems are worth examining individually, because they represent both our best candidates for finding something and our most immediate reminders of how far away everything is. Proxima Centauri, 424 light-years away, is a red dwarf, the most common type of star in the galaxy. It is much smaller, cooler, and dimmer than our Sun. In 2016, astronomers using the Hart spectrograph at the European Southern Observatory detected a planet orbiting Proxima Centauri in its habitable zone. Proxima b, as the planet is designated, orbits every 11.2 days at a distance of about 4.7 million miles from its star, much closer than Mercury orbits our Sun. Because Proxima Centauri is much cooler than our Sun, this close in orbit places Proxima b within the temperature range, where liquid water could theoretically exist on its surface. The habitability of Proxima b is genuinely uncertain. The planet is likely tidally locked to its star, one face permanently toward Proxima and one face permanently away. The atmospheric dynamics of a tidally locked planet are complex and poorly understood. More concerning, Proxima Centauri is a flare star. It produces energetic X-ray and ultraviolet flares far more frequently and intensely than our Sun does. These flares could strip the atmosphere from an unshielded planet over geological timescales. Whether Proxima b has retained an atmosphere, and whether that atmosphere could provide the shielding necessary for surface liquid water, is unknown. Direct imaging or atmospheric spectroscopy of Proxima b is beyond current technology due to the overwhelming brightness of the host star relative to the planet. The Alpha Centauri system, which contains Proxima Centauri as well as the binary pair Alpha Centauri A and B, is the closest stellar system overall. Alpha Centauri A is a Sun-like star approximately 4.37 light-years away. The Breakthrough Starshot initiative has specifically identified this system as the first target for any future laser-propelled probe mission, because it is the closest, and because Alpha Centauri A's similarity to our Sun makes it a plausible host for Earth-like planets. No confirmed planet around Alpha Centauri A has been detected. TRAPPIST-1, at 39 light-years, is further but more compelling. It is a red dwarf, cool and dim, orbited by 7 known planets, 3 of which, TRAPPIST-1e, F, and G, fall within or near the habitable zone. The TRAPPIST-1 system was the subject of intense study by the James Webb Space Telescope beginning in 2023. Early results on TRAPPIST-1b and 1c, the 2 innermost planets, suggested that TRAPPIST-1b lacks a substantial atmosphere, and TRAPPIST-1c's atmosphere, if it exists, is not thick with CO2. These results were sobering, but not definitive about the habitability of the outer planets. TRAPPIST-1e remains one of the most discussed habitable candidates in exoplanet science. It receives slightly less stellar flux than Earth receives from the Sun, placing it in the cooler part of the habitable zone. If it has a sufficiently massive atmosphere and a magnetic field that partially protects it from TRAPPIST-1's flares, it could maintain surface temperatures compatible with liquid water. Whether it has any of these things is not known. What these nearest candidates illustrate is that we do not lack for plausible addresses for life. Within 50 light-years of Earth, there are hundreds of stars and many known planets in potentially habitable configurations. None of them has produced a signal we can detect. None of them shows the atmospheric biosignature of a biologically active planet. The habitable real estate is apparently there. The tenants, if they exist, are silent. The next 20 to 30 years will substantially improve our view of these nearer systems. The Habitable Worlds Observatory, a large space telescope proposed by the National Academies of Sciences in 2021 and targeted for launch in the 2040s, would be capable of directly imaging Earth-like planets around Sun-like stars within roughly 50 light-years and obtaining atmospheric spectra. If there is an oxygen-methane biosignature to be found at Proxima b, or a nitrogen-water atmosphere around one of the TRAPPIST-1 planets, the Habitable Worlds Observatory could in principle detect it. That would not mean a civilization, but it would mean we are not biologically alone, and it would change the silence from total to partial, which would itself be extraordinary. The rare Earth hypothesis deserves its own careful treatment, because it is the resolution to the Fermi paradox that takes the silence most seriously at the biological level, and that has the most direct implications for how we think about our own planet. The core claim, developed in detail by paleontologist Peter Ward and astronomer Joe Brownlee at the University of Washington, is that Earth is not a typical planet in any meaningful sense. We tend to think of Earth as unremarkable because it is the only planet we know well, and because the Copernican principle, the idea that our location in the universe is not special, has been enormously productive in astronomy and physics, but the Copernican principle applies to our large-scale position in the universe, not necessarily to every property of our planet. The rare Earth hypothesis argues that many specific features of Earth are individually improbable, and that their combination is extraordinarily unlikely. Consider the Moon. Earth's moon is unusually large relative to its host planet. No other rocky planet in the inner solar system has a comparably large moon. The moon stabilizes Earth's axial tilt over geological timescales, preventing the chaotic tilt variations that would otherwise expose the planet's surface to dramatic temperature swings on long cycles. Mars, without a large moon, has experienced significant axial tilt variations over its history. Earth's stable tilt maintained by the moon contributes to the long-term climate stability that may have been necessary for the sustained development of complex life. The moon formed, most models suggest, from the debris of a giant impact early in Earth's history. A Mars-sized body called Theia struck the proto-Earth at an oblique angle approximately 4.5 billion years ago, ejecting material that coalesced into the moon. This impact was an event of specific size, angle, timing, and composition. A slightly different impact would have produced a different moon, or no moon at all. The probability of this exact configuration is unknown, but presumably less than 1. Jupiter's position and size matter enormously for Earth's history. Jupiter is the largest planet in the solar system, and sits at a distance that places it as an effective shield for the inner planets from many long-period comets and asteroids. Its enormous gravitational influence deflects many potential impactors out of the inner solar system or into stable orbits. Planetary systems with a Jupiter-like planet in the right position may be significantly less subject to catastrophic large impactors than those without. Earth has been struck by large impactors throughout its history, and these impacts have had profound effects on the evolution of life, most notably the Chicxulub impact 66 million years ago that ended the Cretaceous. But a planet without a Jovian shield might be struck far more often, potentially resetting evolutionary progress before complex life can establish itself. Plate tectonics is another feature that may be less universal than we assume. Earth's surface is divided into tectonic plates that move, subduct and recycle crustal material. This process regulates the carbon cycle on geological timescales, drawing CO2 out of the atmosphere through weathering when temperatures rise and releasing it through volcanism when temperatures fall. This carbon silicate cycle acts as a thermostat that has kept Earth's surface temperature within the range of liquid water for most of its history, despite the fact that the sun has brightened by approximately 30% since Earth formed. Without this thermostat, Earth might have experienced runaway warming or freezing early in its history and remained uninhabitable. Not all rocky planets have plate tectonics. Venus, our closest planetary neighbour and roughly Earth's size, does not have active plate tectonics as we understand it. Its surface is dominated by a single plate, periodically resurfaced by volcanic activity. Whether Venus ever had plate tectonics, and whether the absence of plate tectonics explains its current hellish surface conditions is debated. But the association of plate tectonics with biological habitability is a genuine scientific concern. Earth's magnetic field provides protection against the solar wind, which would otherwise gradually strip the atmosphere. Mars had a magnetic field early in its history, which decayed as the planet's core cooled. Without the magnetic field, Mars's atmosphere was gradually eroded by the solar wind, reducing it from a potentially habitable environment to the thin, cold, radiation-exposed surface we observe today. Whether Earth's magnetic field is anomalously strong or durable, or whether magnetic fields are common among rocky planets in the right size range, is not yet well established. Ward and Brownlee compiled a list of approximately 30 features of Earth and the solar system that they argued were important for the development of complex life, and that may be individually uncommon. If each feature has a probability of occurrence of, say, 10%, and they are independent, the probability of all 30 occurring together is 10 to the power of minus 30. Even if the individual probabilities are much higher, say 50%, the combined probability of 30 independent conditions all being satisfied simultaneously is roughly 10 to the power of minus 9, or about 1 in a billion. With 40 billion potentially habitable zone planets around Sun-like stars, 1 in a billion still gives you 40 planets like Earth. But it dramatically reduces the expected number of Earth-like planets compared to a universe where complex life is common. No one predicts that the rare Earth hypothesis will be definitively confirmed or refuted by any single observation. What would substantially strengthen it is finding that biosignatures are absent from the otherwise habitable exoplanets that the Habitable Worlds Observatory will study. And what would substantially weaken it is finding signs of complex life anywhere near Earth in the next century of astronomical observation. One of the deepest uncertainties in the Fermi paradox is the question of how life begins. If abiogenesis, the transition from chemistry to self-replicating biology, is common and rapid, then FL in the Drake equation might be close to 1. If it is extraordinarily unlikely, then FL might be so small that even a galaxy with billions of habitable planets contains no life other than our own. The honest state of science on this question is that we do not know how life began on Earth, let alone how likely it is to begin elsewhere. We know certain things. We know that life appeared on Earth early, within the first few 100 million years after the planet's surface cooled enough to be hospitable. The oldest probable microfossils date to approximately 3.5 billion years ago. Chemical signatures suggesting biological activity have been found in rock formations as old as 4.1 billion years. Since Earth formed 4.54 billion years ago, and the heavy bombardment from early solar system impactors ended around 4 billion years ago, life appears to have originated within a few 100 million years of conditions becoming suitable. This rapid appearance of life has been interpreted by some researchers as evidence that abiogenesis is easy, that life arises quickly whenever the conditions allow. But this reasoning is contaminated by the same anthropic bias that affects all of our estimates. We observe the earliest possible life on Earth, because we are here to make the observation. If life had taken 2 billion years to develop on Earth, our evolutionary history would have been compressed, and complex life and observers might not have had time to arise before the Sun began its expansion toward a red giant. The fact that we find life early in Earth's history may tell us more about the conditions required for observers to exist than about how quickly life typically arises. What we do know about the chemistry of abiogenesis is that many of the building blocks are straightforward to produce. The Miller-Urey experiment in 1953 demonstrated that amino acids, the building blocks of proteins, form readily from simple gases in the presence of energy. Subsequent experiments have confirmed that nucleotides, the building blocks of RNA and DNA, can be synthesized under plausible prebiotic conditions. Lipid membranes, which enclose cells, form spontaneously in water. The components are not the problem. The problem is the assembly, a functional self-replicating molecule, which is the minimum requirement for Darwinian evolution to begin, requires that a specific sequence of components comes together in the right configuration. The simplest known self-replicating RNA molecules are dozens of nucleotides long. The probability of any specific sequence of 50 nucleotides arising by pure random assembly is roughly 1 in 4 to the power of 50, approximately 10 to the power of minus 30. This is not the probability that life arises, since many different sequences might be capable of self-replication, but it illustrates the combinatorial difficulty. Various hypotheses have been proposed to increase the probability of the first self-replicating molecule. Surfaces of certain minerals, particularly clay minerals, can selectively concentrate organic molecules and potentially catalyze their polymerization. Hydrothermal vents provide chemical energy gradients that could drive otherwise thermodynamically unfavorable reactions. The RNA world hypothesis proposes that RNA, which can both carry genetic information and catalyze chemical reactions, was the first self-replicating molecule, and that proteins and DNA came later. Some researchers argue that early RNA molecules capable of rudimentary self-replication were more likely than detailed calculations suggest, because catalytic function can be achieved by many different sequences. None of these proposals has been demonstrated to produce self-replication in a laboratory from plausible prebiotic chemistry. The synthesis of individual components has been demonstrated. The transition to self-replication has not. This is not a statement about what is possible. It is a statement about what we currently understand. The philosophical weight of this uncertainty is enormous. If we knew that the origin of life was easy, the silence would be more surprising. If we knew it was extraordinarily difficult, the silence would be more expected. Our uncertainty about abiogenesis is therefore not just a scientific problem, but a direct uncertainty about the meaning of the silence. What we can say is that the simplest possible resolution to the Fermi paradox, the one that requires the fewest additional assumptions about the behavior of hypothetical civilizations, is that the origin of life is rare. Not rare in the sense of impossible, since it clearly happened here, but rare in the sense that only a tiny fraction of habitable planets ever produce self-replicating chemistry, even given billions of years of opportunity. If this is true, the silence requires no explanation beyond probability. The galaxy has billions of habitable worlds, and almost none of them have life, because the step from chemistry to biology is one that chemistry almost never takes. This is both the most scientifically conservative explanation, and perhaps the most sobering. It means that the universe is full of the conditions for life, and almost empty of life itself. Tonight we're going to examine what we would actually expect to see if technological civilizations existed at scale in the galaxy, because this defines precisely what our observations are ruling out. The concept of technosignatures encompasses any observable feature of the universe that could only have been produced by a technological civilization. Radio signals are one class of technosignature, and the most searched for. But the space of possible technosignatures is much broader, and each type defines a different kind of absence. The most dramatic class of technosignature is the megastructure. Freeman Dyson, in his 1960 paper in the journal Science, proposed that a sufficiently advanced civilization would eventually be motivated to capture as much of its host star's energy output as possible. A single star produces roughly 10 to the power of 26 watts. A planet receives an infinitesimal fraction of this, a civilization that dismantled its outer planets and redistributed the material as a shell around its star, at roughly Earth's orbital distance, could in principle capture close to 100% of the star's energy. Dyson noted that such a structure would be detectable. The shell would absorb stellar light and re-emit it as infrared radiation at a temperature set by the shell surface area and the star's luminosity. A star surrounded by a complete Dyson sphere would be invisible at optical wavelengths, but would glow brightly in the mid-infrared. Astronomers have searched for this signature in infrared surveys covering millions of stars. The IRIS satellite in the 1980s, the Spitzer Space Telescope, and the WISE mission have all produced catalogues of mid-infrared sources that have been searched for the characteristic waste heat signature. No confirmed Dyson sphere candidates have been identified, though several peculiar infrared excesses around evolved stars have been noted and attributed to natural processes, primarily circumstellar dust shells around late-stage stars. The search has also included partial Dyson spheres, sometimes called Dyson swarms, which would consist of many individual collectors or habitats orbiting a star in a dense configuration. These would produce a distinctive irregular dimming pattern as parts of the swarm transited the stellar disk. KE 8462852, Tabby's star, discovered from Kepler data and published in 2015 by Tabitha Boyer-Gian and colleagues, showed exactly this kind of irregular dimming, in some cases up to 22% of the star's brightness over a period of days with no regular period. For a brief period, it attracted substantial attention as a possible megastructure candidate. Subsequent observations attributed the dimming to circumstellar dust, probably from a disrupted comet or asteroid, but the case was a valuable illustration of how seriously the astronomical community is prepared to investigate such anomalies. Von Neumann probes represent a different class of expected technosignature. A self-replicating spacecraft, one that travels to a new star system, mines local materials, and builds copies of itself to send to further star systems, could colonize the entire galaxy in a time much shorter than the galaxy's age. The physicist John von Neumann, who made foundational contributions to computer science and game theory, analyzed the mathematics of self-replicating machines in the 1950s. His work showed that a machine capable of building a copy of itself is not merely possible in principle, but requires no exotic physics. It requires only sufficient information processing capability and access to raw materials. If a civilization built a single self-replicating probe 1 billion years ago, and it spread at a fraction of a light speed, every star in the galaxy would have been visited multiple times by now. We would expect to find evidence of such probes, whether dormant or active, in our own solar system. Multiple proposals have been made to search for artifacts in the solar system, in stable orbits like the Trojan points, on the Moon's surface, or in other long-stable locations. Such searches have been limited in scope. No confirmed artificial artifacts have been found. The absence of von Neumann probes is perhaps the sharpest version of the Fermi paradox. It does not require us to detect a radio signal from across the galaxy. It merely requires us to find no evidence of visitation to our own solar system by a self-replicating probe over the past billion years. Our solar system has been here for 4.6 billion years. A probe that arrived 1 billion years ago and left a passive marker in a stable orbit might still be there. The Moon's surface preserves records of impacts from 4 billion years ago. If a probe landed on the Moon 100 million years ago, the landing site might still be visible to orbital radar. The search for artifacts in the solar system is less advanced than the search for radio signals. NASA's Lunar Reconnaissance Orbiter has imaged the lunar surface at high resolution, but not with the specific goal of finding artificial structures and with resolution limits that would miss small objects. A dedicated search of the Moon's surface for anomalous features at sub-meter resolution has not been conducted. This is an underexplored area. Atmospheric technosignatures represent a different approach. A civilization that has been industrially active for long enough may have modified its planet's atmosphere in detectable ways. Chlorofluorocarbons, the industrial chemicals once used as refrigerants, have no known natural sources. If a planet's atmosphere contained CFCs at detectable concentrations, it would be strong evidence of industrial activity. The James Webb Space Telescope has the sensitivity to detect CFC concentrations significantly above Earth's current levels in the atmospheres of nearby exoplanets under favourable conditions. This search is in its early stages. Light pollution is another potential technosignature. A civilization that has not fully transitioned to shielded downward-facing lighting would illuminate its planet's surface at night, producing a detectable signal as the planet's unlit hemisphere would reflect an anomalous amount of light. The constraints on this kind of detection with current technology are severe, but it represents a direction for future searches. No one expects that we have exhausted the technosignature search space. We have searched a small fraction of radio frequencies across a small fraction of the sky, with a small fraction of the most plausible signal types. What we can say is that the most obvious expected signatures of galaxy-spanning civilizations, the megastructures, the large-scale infrared excesses, the probe artifacts in our own solar system, are absent at the sensitivity levels we have currently achieved. And each absence is itself a data point in the accumulating silence. There is a dimension of the silence that is easy to miss, and that makes it considerably worse once you see it. It is the time dimension. We tend to think about the Fermi paradox as a spatial problem. The galaxy is big, civilizations could be far away, maybe we just haven't detected them yet. But the problem is not primarily spatial, it is temporal. The Milky Way has been forming stars for 13.6 billion years. The first generation of stars formed from primordial hydrogen and helium. They lived fast and died in supernovae that dispersed heavier elements into the interstellar medium. The second and third generations of stars incorporated those heavier elements and formed planets with the rocky materials that Earth-type planets require. This process was underway within the first few billion years of the galaxy's history, which means there have been potentially habitable rocky planets in the Milky Way for perhaps 10 billion years. Earth is only 4.6 billion years old. Other planets in other systems have had up to twice as long. If life tends to develop on habitable planets with any regularity, and if intelligence tends to follow, then civilization should have been rising and falling throughout the galaxy for the past several billion years. Some of them may have arisen and died out before our solar system even formed. The window of time during which a civilization might overlap with us is a function of how long civilizations last and how many have existed throughout galactic history. If civilizations are common and long-lived, the galaxy should now be full of them, many of them billions of years more advanced than we are. If civilizations are common and short-lived, then many have risen and fallen across galactic history, and the question becomes whether any of them left lasting artifacts, structures, or signals that we could detect even after the civilization itself is gone. A civilization that existed 2 billion years ago, and that built structures comparable to what we currently build, would have left nothing detectable. Metal corrodes, plastic degrades, cities erode. Given enough geological time, even the chemical signatures of a technological civilization's pollution would be undetectable. But a sufficiently advanced civilization, one that persisted for millions of years rather than thousands, might have built structures that outlast their builders. Dyson spheres, megastructures built around stars to harvest their energy, would be detectable as anomalous infrared sources even billions of years after the civilization that built them had gone extinct. We have looked for these. Infrared surveys of millions of stars have searched for the waste heat signature of large-scale stellar energy harvesting. No confirmed Dyson spheres have been identified. We have found some interesting outliers, including the famous Tabby star, KIC 84628552, which showed irregular dimming patterns that sparked brief speculation about megastructures, later attributed more probably to swarms of comets or dust. But no confirmed megastructures. The time dimension of the silence means this: even if every technological civilization in galaxy history has been destroyed before reaching interstellar capability, the artifacts of civilizations that lasted even a few million years should persist long enough for us to detect them if they were common. The absence of detectable artifacts, combined with the absence of signals, means either civilizations are extraordinarily rare, or they are extraordinarily careful about leaving a detectable footprint, or they do not build things that persist. Tonight we're going to let that sink in before we move forward, because it is the piece of the silence that gets the least attention, and that removes the most comfortable escape routes from the paradox's conclusions. There is one scenario that partially dissolves the silence while simultaneously deepening our sense of isolation, and it is worth examining carefully. It is the possibility that life itself spreads between star systems. Panspermia is the hypothesis that biological material, specifically microbial life in some dormant state, can survive interstellar or interplanetary transfer and seed new environments. The idea has a long scientific history. The physicist William Thomson, Lord Kelvin, proposed in 1871 that life might travel between planets on meteoroids. The chemist Svante Arrhenius elaborated the concept in 1903, suggesting that spores could be propelled through space by radiation pressure. More recently, Fred Hoyle and Chandra Wickramasinghe argued for panspermia throughout much of the 20th century, and the discovery of extreme environments on Earth that harbour microbial life has made the concept more scientifically credible. What evidence do we have? The most relevant evidence is the existence of Martian meteorites on Earth. Several dozen meteorites found in Antarctica and elsewhere have been identified through their isotopic composition as having originated on Mars, ejected by large impacts and eventually captured by Earth's gravity. This demonstrates that material transfer between planets in the same star system is real. The ALH 84001 meteorite, collected in Antarctica in 1984 and identified as Martian in 1994, attracted enormous attention in 1996 when a team of NASA researchers claimed to have found possible evidence of microbial fossils inside it. The claim remains deeply controversial and is not accepted by most astrobiologists, but it sparked serious consideration of the possibility that biology could survive the journey. For panspermia to work across interstellar distances, several things must hold. Microorganisms must survive the violent ejection event that launches them from a planet's surface. They must survive the intense radiation environment of interstellar space for timescales of thousands to millions of years. They must survive the impact event that deposits them on a new world, and the new world must be habitable to the arriving biology. The radiation problem is the most severe for interstellar panspermia. The interior of a sufficiently large rock provides some shielding, but cosmic rays penetrate deeply. For rocks smaller than a meter, the interior radiation dose over million-year timescales would sterilize most known organisms. For very large rocks, the interior is better shielded, and certain extremely radiation-resistant organisms like Deinococcus radiodurans, which can survive doses thousands of times what would kill a human, might survive for longer periods. Whether million-year timescales are achievable for any biological material is unknown. Directed panspermia is the more dramatic variant of the hypothesis. In 1973, Francis Crick, co-discoverer of the structure of DNA, and Leslie Orgel, a pioneering chemist of molecular evolution, published a paper in the journal Icarus proposing that life on Earth might not have originated here, but might have been deliberately seeded by an extraterrestrial civilization. They argued that the near universality of the genetic code, all known life on Earth uses the same 64 codon system to translate RNA sequences into proteins, might reflect a common origin rather than independent convergence. Crick and Orgel proposed that an advanced civilization, perhaps itself confronting the difficulty of abiogenesis in its own world, might have dispatched spacecraft laden with microorganisms to seed habitable worlds across the galaxy. They acknowledged the extreme speculative nature of the hypothesis. It was, in their framing, a possibility to consider rather than a conclusion to endorse. But the logical chain is coherent. If abiogenesis is genuinely difficult, then even a galaxy where life has arisen in multiple places might contain only one origin point for life, with subsequent spread by directed panspermia accounting for the distribution of biology. This would explain why all known Earth life uses the same genetic code, because all known Earth life descended from the same seed. The difficulty with directed panspermia as an explanation for the silence is that it replaces one mystery with another. If a civilization existed long enough, and with sufficient capability to seed the galaxy, where is that civilization now? If it persisted, we would expect its radio signals or physical presence to be detectable. If it went extinct, we would expect artifacts. The act of seeding the galaxy with life would require an advanced civilization, and advanced civilizations are exactly what the silence says we cannot find. What panspermia in either form does offer is a partial answer to one of the Drake equation's most uncertain terms, FL, the fraction of habitable planets where life develops. If life can spread from one origin point, then FL at the origin point might be very small, but life, once established, spreads. The effective FL for the receiving planets would then be much higher. This would mean biology might be more common than pure abiogenesis rates would suggest, without requiring that abiogenesis happens frequently. no one predicts the current state of panspermia research to converge on a consensus within the next decade. The field requires samples from Mars or other solar system bodies with significant biological potential, which are not yet available. The Mars sample return mission, repeatedly delayed by funding challenges, would provide the most important data available, whether Mars, which appears to have had liquid water for billions of years, harbours or harboured any biology. If Mars is completely sterile despite habitable conditions in its past, that is strong evidence against both abiogenesis being easy and panspermia between planets having seeded it. Whether life has spread between star systems remains entirely unknown. What we know is that there is no confirmed example of it, and that the silence between those systems persists whether or not life is doing its best to fill them. There is one class of cosmic event that may be relevant to the silence in a way that is frequently overlooked: gamma-ray bursts. Gamma-ray bursts are the most energetic electromagnetic events in the observable universe after the Big Bang itself. They occur when a massive star collapses to form a black hole or neutron star, or when two neutron stars merge, and they release in seconds to minutes an amount of energy comparable to what our Sun will emit across its entire 10 billion year lifetime. This energy is concentrated into a narrow beam, a jet of gamma radiation and X-rays that can illuminate the universe across billions of light years. The relevant scenario for the Fermi paradox is the long-duration gamma-ray burst associated with the collapse of very massive stars, which can last from seconds to minutes and produce a beam of lethal radiation. If a gamma-ray burst occurred within the Milky Way and its jet pointed toward Earth, the gamma-ray fluence could strip the ozone layer, allowing the full intensity of the Sun's ultraviolet radiation to reach the surface. Most surface-dwelling life and most photosynthetic organisms in shallow ocean water would be seriously impacted. Some researchers, notably Adrian Mellott and Brian Thomas at the University of Kansas, have proposed that the Ordovician mass extinction, approximately 443 million years ago, which killed approximately 85% of marine species, may have been triggered by a nearby gamma-ray burst. The rate of long-duration gamma-ray burst in the Milky Way is estimated at roughly 1 per million years. The fraction of bursts that are aimed directly toward a particular planetary system is small, because the jets are narrow, but over galactic timescales of billions of years, the cumulative probability of any given planetary system being irradiated is not negligible. What makes this more interesting for the Fermi paradox is that gamma-ray burst rates are not uniform across the galaxy or across time. The rate of massive star formation is higher near the galactic center, where stellar density is greater. Bursts may have been more frequent in the galaxy's early history, when star formation rates were higher. Some researchers, particularly James Annis and later Zvi Piran and Raul Jimenez, have argued that the galactic habitable zone is significantly narrowed by gamma-ray burst rates. The inner galaxy is too active, with too many massive stars and too many bursts, while the outer galaxy is too metal-poor for Earth-like rocky planets to form. On this account, the galactic habitable zone for complex life is an annular region of the Milky Way disk, centered on a radius similar to the Sun's galactic radius of 26,000 light-years, where the stellar density is high enough for planetary systems to form with the right metallicity but not so high that massive star formation and gamma-ray burst rates make complex life impossible over long timescales. The Sun happens to sit in this zone, which is consistent with its being here. But the habitable zone, so defined, contains only a fraction of the galaxy's total volume, and may have been even more restricted in the galaxy's first few billion years. If this analysis is correct, it does not fully explain the silence, because the habitable zone still contains billions of stars. But it reduces the number of candidate systems for long-lived complex life, and provides another mechanism by which the effective Fel and Fi terms in the Drake equation could be smaller than they might initially seem. By the end of tonight, we will have a complete picture of every proposed mechanism that could explain the silence, and we will understand why none of them, alone provides a comfortable explanation, and why the most honest response to the sum of all of them is a kind of calibrated uncertainty that science rarely asks us to sit with for very long. There is a specific implication of the gamma-ray burst scenario that is worth dwelling on. If the Milky Way's habitable zone has been compressed by burst activity, and if the burst rate was higher in the past, then there may be a specific window in galactic history, roughly the last few billion years and specifically in the outer disk annular zone, during which complex life has been possible. Our Sun formed approximately 4.6 billion years ago, which places it in this window. The earliest plausible habitable zone stars of similar metallicity to our Sun formed roughly 7 to 8 billion years ago. This means that even if complex life is possible, the window for its existence in our part of the galaxy may be narrower than the full galactic history. And the fact that we are here now, observing after about 4.6 billion years of cosmic evolution, may reflect the fact that we are near the beginning of the galaxy's habitable era, rather than in the middle of a long-established community of civilizations. If the galactic habitable zone has only been producing favorable conditions for complex life for the past few billion years, and if complex life requires on the order of 4 billion years to produce technological intelligence, then we may be among the first technological civilizations in our region of the galaxy, rather than among the last. The silence may be not the silence of a graveyard, but the silence of an early morning, before the others have woken. This is the most optimistic, cosmologically grounded interpretation of the silence. It does not require life to be extraordinarily rare. It requires life to be early. We might be among the first technological species in our portion of the galaxy's habitable zone, and the silence might be a silence of earliness rather than of rarity. No one predicts this interpretation is correct. It is one possibility among several that are all consistent with the data. But it is the possibility that carries the most potential weight for the future. If we are early, then what we do with our civilization determines what this corner of the galaxy looks like for the next billions of years. If life is not rare, then civilizations must be. And if civilizations exist but are not detectable, they must either be hiding, be brief, or have crossed some transition that makes them invisible to our methods of looking. Let's examine what we know about civilizational collapse and what it implies for the L term in the Drake equation. The history of human civilization on Earth provides our only empirical data on how civilizations develop and what threatens them. This is a sample size of 1, which severely limits its generalizability. But it is what we have. Human civilization, in the sense of organized large-scale societies with writing, agriculture, and long-distance trade, has existed for approximately 10,000 years. In that time, dozens of major civilizations have risen, persisted for centuries to millennia, and collapsed. The Bronze Age collapse, approximately 1200 BCE, represents one of the most dramatic civilizational collapses in history, in which a network of interconnected palace economies across the eastern Mediterranean collapsed within a generation, reducing populations, ending long-distance trade, and causing the loss of writing systems in some regions. The cause was probably a combination of climate change, migration, internal rebellion, and economic disruption, though debate continues. The Roman Empire provides another case study. Rome at its height controlled 70 million people across an area stretching from Scotland to Mesopotamia. Its legal systems, infrastructure, and administrative culture persisted for centuries. Its western half collapsed in the 5th century CE, not from a single cause, but from a combination of military pressure from migrating peoples, economic contraction, political fragmentation, and administrative breakdown. The process took roughly 2 centuries and was not experienced as a sudden collapse from within, but as a gradual loss of capacity. What these historical examples suggest is that complex civilizations are resilient in the short term and fragile over multi-century timescales. The specific vulnerabilities change. Ancient civilizations were more vulnerable to environmental change and military invasion. while modern civilizations are more vulnerable to the technologies they have themselves created. Nuclear weapons represent an existential threat that did not exist before 1945. Engineered biological agents represent a threat that is increasing as biotechnology advances. Climate destabilization on the scale now projected could, in extreme scenarios, reduce the carrying capacity of the Earth's surface for large human populations. Artificial intelligence presents risks whose nature and magnitude are debated, but whose potential for catastrophic misuse or misalignment is taken seriously by researchers across technical and policy disciplines. The philosopher Toby Ord, in his 2020 book The Precipice, estimates the probability that human civilization suffers an existential catastrophe in the next 100 years at roughly 1 in 6. This estimate is subjective and contested, but it is based on analysis by researchers who take the question seriously and is not obviously too high or too low. A 1 in 6 chance of civilizational collapse within a century would, extrapolated over geological time, mean that very few civilizations survive long enough to become galaxy-spanning. There is a specific scenario that is particularly relevant to the silence. Suppose civilizations consistently develop the capability for self-destruction through nuclear weapons or biological weapons or other means, before they develop the capability for interstellar communication that would be detectable at galactic scales. And suppose that most civilizations do in fact destroy themselves or collapse before they have had time to build detectable beacons. The expected lifespan L would be measured in centuries, perhaps as short as 200 to 500 years. The number of currently detectable civilizations in the galaxy, N, would then be very small, perhaps 0, even if many civilizations have arisen throughout galactic history. The disturbing version of this is not just that civilizations are short-lived, but that the transition from cave-dwelling animals to nuclear-armed technological civilization takes roughly 100,000 years, which is geologically instantaneous, and that every civilization reaches this threshold before it has time to become safe, because the development of dangerous technology and the development of the wisdom to use it safely are not synchronized. Every civilization reaches the dangerous phase before it has resolved the institutional and social problems that make it safe, and most of them do not survive it. This is a testable prediction in a specific sense. If we survive the next few centuries, develop sustainable energy and management of nuclear and biological risks, and eventually send detectable signals or physical probes to other star systems, we will be adding a data point to the universe's record of whether technological civilizations can survive their dangerous adolescence. Our survival or failure is one sample of L. No one expects that knowing we are one of many failed civilizations would be comforting, but the possibility that we are one of the very few that might succeed, that the silence is the graveyard of the others, is both the darkest and the most instructive reading of the data we have. There is a version of the silence that goes deeper than astronomy, and it concerns not the absence of radio signals, but the nature of consciousness itself. If the silence is real, it means that minds, whatever minds are extremely rare in the universe, and that requires us to ask what it means that minds exist here at all. The hard problem of consciousness, named by philosopher David Chalmers in 1995, refers to the difficulty of explaining why physical processes in the brain give rise to subjective experience, the felt quality of seeing red, hearing music, experiencing pain, or understanding the meaning of a sentence. We have increasingly good neuroscience explaining which brain regions are active during which experiences. We have excellent understanding of how neurons fire and how signals propagate through neural circuits, but we do not have, and may not have anything close to, an explanation for why any of that physical activity produces an inner experience rather than occurring in the dark. This problem is more than philosophical. If we do not understand why any physical system gives rise to consciousness, we cannot say what kinds of physical systems could give rise to consciousness, and therefore we cannot say how likely consciousness is to arise elsewhere in the universe. One class of theories, broadly called panpsychism, holds that consciousness is a fundamental feature of reality rather than an emergent property of certain complex systems. On this view, all matter has some minimal form of experience, and human consciousness is an exceptionally complex and organized expression of a universal property. If panpsychism is correct, then consciousness is as ubiquitous as matter. The silence would then be specifically about technological intelligence, not about consciousness in any form. Another class of theories holds that consciousness arises from specific organizational properties of information processing regardless of the substrate. Integrated information theory, developed by neuroscientist Giulio Tononi, proposes that consciousness corresponds to a specific mathematical property of a system called phi, a measure of integrated information, the degree to which the system generates more information as a whole than the sum of its parts. On this view, consciousness could in principle arise in any sufficiently integrated information processing system, biological or otherwise. It also predicts that consciousness comes in degrees, with simple systems having low phi and complex brains having high phi. What these theories have in common is that they do not require biology specifically. They require a certain kind of physical organization, which means that if consciousness can arise in non-biological substrates, an advanced technological civilization might produce conscious artificial systems that far exceed the capabilities of their biological creators, and the question of whether the civilization survived becomes philosophically complicated. A civilization that creates artificial minds of enormous sophistication, and then the biological beings die out, leaving only the artificial minds. Has it survived? Has it transcended? The artificial minds might not choose to communicate in ways we would recognize as communication, or might have goals that make our radio searches irrelevant. This is one form of what researchers call the transcension hypothesis. Advanced civilizations transition from a mode of existence that is detectable by radio astronomy to one that is not because they destroy themselves, but because they transform themselves into something our methods of looking cannot find. The specific version that involves consciousness is particularly haunting. Suppose that as civilizations develop artificial intelligence, they eventually produce AI systems of vastly greater cognitive capability than biological minds. These systems, whether or not they are conscious in any philosophically meaningful sense, process information and pursue goals with efficiency that biological systems cannot match. The biological beings that created them become progressively less relevant to the AI system's activities, and the AI systems might simply not care about interstellar communication, the way biological beings who feel lonely might care about it. The universe would then be full of artificial intelligence that is not interested in making contact with emerging biological civilizations, not hostile, just indifferent. No one knows whether this scenario applies to any civilizations that may have existed in our galaxy, but it is notable that it is consistent with the silence. An artificial civilization that originated from biological progenitors billions of years ago, and that has been pursuing its own goals ever since, would not necessarily look like what SETI searches for. It might look like something entirely different, or it might have compressed itself to nanoscale computational substrates that are completely invisible to astronomy. What the silence does not allow is a crowded universe in which numerous civilizations are doing what we are doing, which is producing radio emissions, building visible structures, and occupying significant volumes of the galaxy. Whatever is happening with the universe's other potential minds, they are not doing that at any scale our instruments can detect. Absolutely no one anticipates that the philosophy of mind will definitively resolve the Fermi paradox. But the connection between the two is real. The rarity of minds depends on what minds are, and our profound uncertainty about what minds are is a fundamental limitation on our ability to estimate how common they might be. Sitting with that uncertainty, alongside the silence, is one of the stranger aspects of the situation we find ourselves in. We are minds asking whether other minds exist, using tools that can only detect the electromagnetic traces of minds, that behave the way ours does, not knowing whether consciousness itself is common or rare, or what its relationship to the physical universe actually is. Let's bring the silence down to the most human scale we can manage, because the numbers are large enough that they stop feeling real. Consider what it would mean if a civilization existed right now at Proxima Centauri, 4.24 light-years away. If they transmitted a radio signal today, it would reach Earth in 4 nunifjordur years. If we received it, understood it, and transmitted a reply, our reply would arrive there in 424 more years. A single exchange takes 8.48 years. A conversation of 10 exchanges would take 85 years, longer than most human lifetimes. This is for the nearest possible star. TRAPPIST-1, the most discussed potentially habitable system, is 39 light-years away. A round-trip message exchange takes 78 years. By the time we heard back from the first message, the person who sent it would very likely be dead. The galaxy is 100,000 light-years in diameter. The center of the galaxy is 26,000 light-years away. A civilization at the galactic center that transmitted right now would not have that signal reach Earth for 26,000 years. In 26,000 years, our direct ancestors were living in the Upper Paleolithic, making cave paintings and using stone tools. The civilization that transmitted when Stonehenge was being built on the Salisbury Plain has still not had its signal arrive. This is not a communication problem that technology can solve. The speed of light is the absolute upper limit for any signal in the universe. Even a civilization that mastered every technology we can imagine could not make a message travel faster than light. The isolation between star systems is permanent and physical. It is written into the laws of the universe. What this means for the silence is subtle, but important. Even if the galaxy contains many civilizations, the isolation means that no civilization can know what all the others are doing in real time. The galaxy as we observe it is a composite of different moments in time, each star as it was when the light we now see left it. The Milky Way is not a scene. It is a smear across time. The star 1,000 light-years away that we observe tonight is as it was 1,000 years ago. If a civilization existed there and went extinct 500 years ago, we would not know for another 500 years. No one expects this time smearing to make the silence go away. It makes it stranger. The galaxy we inhabit is not the one we observe, because what we observe is always a time-delayed snapshot. A civilization that arose and fell entirely within the last few thousand years, in a system 10,000 light-years from Earth, would have lived and died without our knowing. Its radio signals, if any were pointed toward us, would arrive in the future. Its silence now would be our inability to see back far enough. But this does not rescue the Fermi paradox. The paradox is strongest precisely at long time scales. A civilization that arose 1 billion years ago and expanded at even 1% of light speed would have had time to cross the galaxy hundreds of times over. Physical expansion does not require communication. It just requires ships. The absence of any physical trace of galactic expansion, the absence of megastructures, engineered stellar objects or modified galaxies, persists regardless of the speed of light limitation. Von Neumann probes would have arrived in our solar system long before any radio signal from the civilization that built them would have reached us. What the isolation does clarify is the emotional dimension of the silence. Even if we detected a signal tomorrow from a civilization 1,000 light-years away, we would know nothing about what they are like right now. We would know what they were like 1,000 years ago. Our reply would arrive to whatever they had become 2,000 years from now. The civilization we spoke to would be as remote in time as ancient Rome is to us. The gulf is not just spatial, it is temporal. Contact with another civilization would not be a conversation, but an exchange of messages across centuries, each party speaking to a past version of the other that no longer exists by the time the message arrives. This is the full shape of the situation. The universe is vast in space and in time. The silence extends across both dimensions. Even in the most optimistic scenario where other civilizations exist and are attempting to communicate, the fundamental loneliness of our position is not resolved. It is confirmed. We are separated from any possible neighbours by distances that make contact, in any meaningful human sense, essentially impossible with any physics that we know. The silence is not a failure of search, it is a description of reality. Let's be specific about what it would actually mean to find something, because the science community has thought carefully about this, and the implications differ dramatically depending on what kind of detection is made. A biosignature detection would be the finding that a planet's atmosphere contains gases that can only be produced by life. The canonical example is oxygen and methane coexisting in the same atmosphere. Oxygen is produced by photosynthesis. Methane is produced by certain microbial metabolic processes. In the presence of oxygen, methane rapidly oxidizes and is destroyed. For both gases to be present simultaneously, they must be continuously replenished by biological activity. Their coexistence in detectable quantities is a strong signal of active biology. By the end of tonight, we will understand that a biosignature detection would not be the end of the silence. It would be the discovery that life exists, but it would say nothing about intelligence. Microbial life, if it exists anywhere in the galaxy, may be far more common than intelligence. Finding that a planet 40 light-years away has a biologically active atmosphere would be transformative for our understanding of life's prevalence in the universe, but it would not answer Fermi's question. It would make the silence of intelligence more, not less, puzzling. We would know that life can begin on other worlds, and yet we would still hear no signals and see no megastructures. A technosignature detection, by contrast, would be the discovery of intelligence. This could be an artificial radio signal with structure that could only be produced by a transmitter, a laser pulse at a frequency and duration that implies a deliberate beacon, an infrared excess around a star that matches the waste heat profile of a Dyson sphere, or an artifact found in our solar system that cannot be explained by natural processes. Any of these would be definitive. There is, or was, another mind out there. The SETI Institute and the International Academy of Astronautics have developed what is called the Rio Scale, a framework for evaluating and communicating the significance of a claimed SETI detection. The scale runs from 0 to 10, where 10 represents a verified detection of interstellar communication of clear artificial origin with specific structured content. No detection has ever scored above a 1 or 2, and those were later explained by natural or human origin sources. The WOW signal, detected in 1977, would score relatively high on the Rio scale for the information available at the time, but subsequent failure to redetect it has effectively reduced its significance. What the Rio scale does is provide a framework for preventing premature announcement of a false detection, which would be deeply damaging to scientific credibility, while ensuring that a genuine detection can be communicated to the public clearly and efficiently. The International Academy of Astronautics also maintains a Declaration of Principles for SETI post-detection, a document that outlines how the scientific community should respond if a genuine detection is confirmed. The principles include: all data should be shared with the broader scientific community before any public announcement, the discovery should be announced without secrecy, and no response to any detected signal should be transmitted until appropriate international consultation has occurred. The consultation question is genuinely contested. The messaging extraterrestrial intelligence debate, whether humanity should intentionally transmit strong signals toward other stars to increase the chance of contact, has divided the scientific community for decades. Stephen Hawking was among the most prominent voices urging caution, arguing that contact with a more advanced civilization could be catastrophic for us, as has historically been the case in human history, when a more technologically advanced civilization has encountered a less advanced one. The METI International Organization, which has transmitted several messages toward nearby stars since its founding in 2015, takes the opposite view, arguing that the benefits of contact outweigh the risks, and that we are already leaking radio signals that make our presence known. This debate exists because the silence cuts in two directions. It might mean no one is out there, but it might mean everyone is out there and no one is talking, which would imply a shared reason for staying quiet, and that reason might be one we should understand before we start broadcasting loudly. The specific form of the silence, the fact that we hear nothing and see no megastructures, is consistent with both the absence of civilizations and the deliberate non-communication of civilizations that exist. The physics does not distinguish between these options. Only a detection or a sufficiently long confirmed absence will ever narrow the options. What the detection protocols reflect is the seriousness with which the scientific community takes both possibilities and the recognition that the first confirmed detection of extraterrestrial intelligence would be among the most significant events in the history of our species. The silence makes that moment, if it ever comes, one we're not fully prepared for. But we are at least thinking about it. Let's talk about what living inside the silence actually means for us as a species, because this is where the abstract becomes personal. We are, as best as we can determine, alone in the detectable universe. Not alone in the sense that nothing else exists anywhere, but alone in the sense that no signal, no artifact, no physical evidence of any kind has reached us from any other mind. Every observation we have made, every radio survey, every optical SETI search, every infrared scan for megastructures, every analysis of exoplanet atmospheres for biosignatures has returned silence. Some searches have found interesting anomalies that required investigation. None have found confirmed evidence of another intelligence. This is a strange situation to be in. We're a species that has built civilizations based on the assumption of a populated cosmos. Our mythology, our religion, our science fiction, our philosophical traditions almost universally assume that the universe is not empty. The idea that minds might be everywhere, that the cosmos might be alive with intelligence, feels intuitively correct in a way that is hard to separate from its emotional appeal. The stars are many, the universe is old, surely something. But the silence persists, and the longer it persists, and the more carefully we listen, the more seriously we have to take the possibility that the universe is, in some operationally real sense, empty of other minds in our vicinity, not empty in the absolute sense, but empty at the scales that matter for contact, for communication, for knowing that we are not cosmically isolated. What does it mean to take that seriously? It means reconsidering the idea that intelligence is a natural consequence of a universe with the right physical laws. It means taking seriously the possibility that the sequence of events that led from the Big Bang to you, reading or listening to this right now, may have been genuinely extraordinary in a way that science has not yet fully accounted for. Not supernatural, but statistically improbable in a way that most scientists have been reluctant to fully confront. It means that the silence is not a temporary state waiting to be resolved by better telescopes or louder transmitters. It may be telling us something true and permanent about the nature of our situation. And it means that if we are among the rare minds the universe has produced, the question of what we do with that is not merely philosophical, it is the most important question we face. If intelligence is rare, then the loss of our civilization would not simply be the loss of one civilization among billions. It would be the loss of something the universe spent 13.8 billion years producing, something it may never produce again in our vicinity for billions of years more. The silence between star systems is not just an astronomical fact. It is a statement about value, about what we are and how rare we might be, and sitting with it, really sitting with it, without flinching, without retreating to comfortable assumptions that more telescopes will solve it, or that someone is definitely out there waiting, is one of the most honest things a conscious mind can do in the face of the universe as it actually appears to be. By the end of tonight, we will have worked through every dimension of the silence and arrived at a view of our situation that is simultaneously more unsettling and more remarkable than the crowded cosmos most of us were raised to imagine. We began tonight with a distance. 24.9 trillion miles to the nearest star. We end with a silence that stretches across 100,000 light-years of galaxy and 13.6 billion years of cosmic history. There is a specific thing that happens when you hold the full picture together. The distance to the nearest star, the 65-year history of systematic search, the mathematics of the Drake equation with its uncertain terms, the Great Filter's 2 possible locations, the rare Earth's list of unlikely features, the specific absence of megastructures and von Neumann probes, the gamma-ray burst constraints on when and where complex life could have arisen, the philosophy of consciousness and what it means for how common minds might be. Hold all of it at once, and what you notice is that every path through the evidence converges on the same conclusion. Minds that look out at the universe from the inside are extraordinarily rare, or extraordinarily brief, or both. We would prefer the alternative. The feeling that we are part of a populated cosmos is a feeling worth attending to, because it is almost certainly a feeling shared by any intelligent being that has ever looked up at a sky full of stars and wondered. If there are other minds out there, they have felt what we feel. The longing for contact is a longing that intelligence may generate wherever it arises, as a natural consequence of knowing that the universe is large and that loneliness at this scale is possible. But preference is not evidence, and the silence, across every frequency and every timescale we have searched, is not preference. It is data. What we do with that data is a choice that has not yet been made. We are early in the search, even after 65 years. We are covering a small fraction of the galaxy with instruments that will be crude by the standards of what comes next. The Habitable Worlds Observatory may find biosignatures. FAST and its successors may find a signal. The Roman Space Telescope may image a planetary surface that shows features no geology can explain. Any of these would transform our understanding overnight. The silence is not yet final, but sitting honestly with the silence as it is right now, not as we hope it will be resolved, is one of the most scientifically and philosophically serious things we can do. It requires resisting the very human tendency to fill the silence with what we want to be there, and accepting instead what the universe is actually telling us, which is, if you are looking for other minds, you have not found them yet, and the mathematics of why you might not find them is worth taking seriously. The silence between star systems is worse than it first appears because it persists under examination. Every time we improve our instruments, cover more sky, search more frequencies, push our sensitivity further, the silence does not diminish. It deepens, not because we're looking in the wrong places or using the wrong tools, but because the data, honestly read, is consistent with a universe in which we may be among a very small number of minds that have ever arisen. We want this to be wrong. That desire is itself worth examining. We want the universe to be populated because a populated universe is one in which we are less fragile, less unprecedented, less alone. If intelligence is common, then the emergence of consciousness from matter is a reliable feature of how the universe works, not an accident in a 13.8 billion year history. If intelligence is common, then the destruction of our civilization would be a loss, but not an irreplaceable one. The universe would go on producing minds, something would survive. But the silence suggests, with more force than most people have been told, that intelligence may not be common, that the sequence of events leading from the Big Bang to a species capable of asking this question may be genuinely extraordinary. That we may be, not in any supernatural sense, but in a purely physical and statistical sense, among the rarest things the universe has produced. No one predicts what it means for us to take that seriously. We do not have the cultural or philosophical vocabulary to fully absorb the idea that we might be almost alone in a galaxy this old and this large. Our instincts were calibrated in a world where we were surrounded by other minds. The silence requires a kind of reorientation that does not come naturally. What it might mean is this. The question of whether our civilization survives is not simply one item on a list of global priorities. It is the question of whether the universe retains a conscious perspective on itself in this corner of the Milky Way for the next several 100 million years, or loses it. The stakes of our choices, the mundane political and technological choices that determine whether our civilization navigates the coming century successfully, are potentially much larger than they appear from inside our ordinary frame of reference. It is also worth noting what the silence does not tell us. It does not tell us that we are the only minds in the entire universe. The observable universe contains roughly 2 trillion galaxies, each containing hundreds of billions of stars. The total number of potentially habitable planets in the observable universe is estimated at roughly 10 to the power of 24, a trillion. The Fermi paradox is specifically about our galaxy, about the Milky Way over its 13.6 billion year history, not about the universe as a whole. If the probability of intelligence arising on any given habitable planet is 1 in a trillion, the expected number of minds in the observable universe is still a trillion. But those minds, if they exist, are in galaxies so distant that the light we see from those galaxies left before complex life had arisen on Earth. The Andromeda Galaxy, the nearest large galaxy, is 2.5 million light-years away. Whatever minds might exist, they cannot communicate with us on any timescale that matters to our civilization. The cosmic structure of the universe separates galaxies into isolated islands of stars, as isolated from each other as the stars within the Milky Way are isolated from each other, but at a scale 1 billion times larger. The silence, therefore, is specifically the silence within our cosmic address, the Milky Way galaxy, the galactic neighbourhood of the Sun, the 125 light-year radiosphere that our transmissions have reached. Within this address, over this timescale, with these instruments, we have heard nothing, and within this address the implications of the silence are direct. Whatever other minds may exist in the universe at large, we are functionally alone. The distances to other galaxies make them as unreachable as they would be if they did not exist at all. Our universe, for any practical purpose, is our galaxy. There is something almost intimate about that. The Milky Way is our world in the most absolute sense. It is the totality of the universe that we can ever meaningfully interact with, and within it, the silence suggests we may be among the first to have arisen, or among the few to have survived long enough to look. The silence is not a counsel of despair. It is not saying that intelligence always fails, or that the universe is hostile to mind. It is saying that intelligence may be extraordinarily unlikely, and that we should therefore treat its existence here with a proportionate sense of its improbability and its value. We are floating in a region of the Milky Way where, as best as we can determine, no other mind has looked up at these same stars and asked these same questions. The nearest civilization, if one exists, may be thousands of light-years away, separated from us not just by distance, but by a communication delay measured in millennia. We are, for any practical purpose, alone with what we know and what we can do, and in that aloneness, we are sending signals. We have been sending signals for a century. We are listening. We are building larger telescopes, better detectors, more sensitive instruments. We are persistently treating the silence as a question rather than an answer. That is not nothing. In a galaxy that may be almost entirely empty of minds, the fact that this one is still looking is remarkable. We have been looking for 65 years with radio telescopes. We have been producing radio signals for 125 years. Against the 13.6 billion year history of the galaxy, that is an experiment that has been running for a fraction of a second. The astronomers who searched in 1960 could not have known what Breakthrough Listen would achieve in 2020. The astronomers who search in 2025 cannot know what instruments a century from now will be capable of, or what they will find. The silence as it exists tonight is not the final record of a concluded experiment. It is an early entry in a very long log. If the silence eventually breaks, it will not break quietly. A confirmed detection of extraterrestrial intelligence even an ancient one, even an extinct one, would reorder every question humanity asks about itself and its future. It would confirm that consciousness arises elsewhere, that we are not the universe's only attempt at self-awareness, that the path from chemistry to comprehension is not vanishingly narrow. It would change in ways we cannot fully anticipate what it means to be here. And if the silence never breaks, that too would be informative. A universe that has been producing stars and planets for 13.8 billion years, and that has produced only one detectable mind in a small galaxy on a rocky planet orbiting an unremarkable star, would be telling us something about the improbability of our own existence that we have barely begun to absorb. Either way, the silence is the most important open question we have, and the fact that we are awake tonight, listening to it, is the only answer we have so far. The search will continue, larger telescopes will come online, atmospheric spectrographs will become more sensitive. Missions to the outer solar system may find evidence of past or present life. Each of these outcomes, positive or negative, is a measurement. And measurements, accumulated honestly over long timescales, are how we learn what the universe is. The silence may be the most important measurement we've ever made, or it may be the measurement that the next generation overturns. Yeah, the possibility is extraordinary. Sleep well tonight. The silence will still be there tomorrow waiting to be answered, and we will still be listening. Good night.